Hi, I'm Ricci for Trelleborg Applied Technologies, and I want to talk today about the Eccospheres Hollow Glass Microsphere line for use in dielectric applications. This is a type of application where the Eccospheres were used for many years in radar transparent coatings or low dielectric potting complexes, and you can see it get used a lot more in recent times in copper-clad laminates and 5G equipment, in electrical connectors, and so it's a variant of the applications of Eccospheres that are growing quickly. So let's do an example with the Eccosphere SI130. This is a particle which is 0.13 grams per cc, and we'll assume a particle size of 50 microns for this example. So what that means is when we take a look inside the particle, you can see that the wall thickness is approximately 1 micron, and the internal pore makes up 94% of the volume. And so for this calculation, it's essentially a rule of mixtures to get the dielectric constant of the particle. The wall thickness, the wall material is 99% silica. That's a Eccosphere exclusive property. So, and again, the silica has a dielectric constant of 3.8. The internal gas, we're going to call it 1.0, which is air essentially. And what you get is a net particle dielectric constant of 1.15. So if we play with this a little bit and we increase the wall thickness to 3 microns, the internal pore as a percentage of the volume falls to 83%. The particle density rises to 0.38 grams per cc because the wall is thicker. The material constants remain the same, and the particle dielectric constant rises to 1.45. And so that gives you an example of how you can play with the dielectric constant a little bit within these particles. Now, if you compare that to a commodity-grade glass microsphere with the same shell thickness, the commodity-grade glass microspheres are generally made of soda-lime glass, which is only 70% silica. The other 30% is mostly sodium. And so you can see the particle density rises to 0.44. It's a higher density because the glass actually has a higher density. And the silica making up the wall has a dielectric constant of 7.5, resulting in a net particle dielectric constant of 2.3. Now, it's important to remember this because many formulators, when they're looking for the dielectric constant or they're using a silica particle in their formulation, will kind of Google the dielectric constant of silica and use that. But that's incorrect because most of these particles are not 99% silica like the Eccosphere. They're much lower, resulting in a much higher dielectric constant. So I want to put a pin in that common mistake that's made by formulators. When we look at the impact on formulations for a second, you can see here in the top left that the best way to control particle dielectric constant is via the density, because you're directly changing the proportion of the particle made up between the glass and the internal pore, whereas the dielectric constant stays constant as you change particle size given the same density. And again, this is a very basic example, but this would be called holding a radius ratio static. And now if you feed that data down to a very simple composite formulation, in this case with epoxy, you can see as the density of the particle goes up, the dielectric constant of the formulation goes up, and as the loading goes up, the dielectric constant of the formulation goes down. And that gives you a net design window using epoxy of somewhere between 2.07 and 3.09. Again, you know, the base dielectric constant of the matrix in this case changes with temperature. Largely, it changes with frequency, but this is just a very basic example. PTFE, another very common dielectric matrix resin. You can see the window would be 1.51 to 1.97. And so it's just a great way to control dielectric constant. And again, the great thing about the Eccospheres hollow glass microspheres is they're stable to a very high temperature, and they're stable across frequencies. And so it's just very, very controllable in terms of their properties. The additional advantages of the Eccosphere property, again, this is mainly over commodity grade products, is that we can control moisture content, which has a big impact on the net dielectric constant. Our product has a lower viscosity for the same volumetric addition, which means you can put more of them in. And as you can see in the bottom left chart there, as you put more of them in, your dielectric constant will go down. They're chemically inert, so they won't have bad interactions with resin systems. Most of the commodity grade products have a sulfurous internal gas, which will corrupt silicone resin systems. and also cause other issues. And of course, that sodium in the commodity glass leaches out and cross-reacts with resins in a deleterious manner. They're higher strength, they're customizable. We can customize particle size, we can customize packaging, specification, and of course, they're lighter weight for the same density. And so that's a very basic look at dielectric constant when it comes to the Eccospheres, hollow glass microspheres. Thank you for your time. I'm Ricci for Trelleborg Applied Technologies, and this has been a discussion about Eccospheres, hollow glass microspheres for dielectric applications. So if you have any new applications in electrical connectors, radar transparent coatings, circuit board materials, copper clad laminates, we'd love to talk to you about what Eccospheres can bring to your formulation. Thank you.